Okay, so I hope you're able to get all those answers to match with the pi electrons for the DNA base pairs confirming they are indeed aromatic. Let's take a minute to, DNA is amazing enough, it deserves a little more time. 3D model, look what's going on there. So I don't know how many models of DNA you've looked at, but when you get really zoomed in on the part that's interesting to us chemists, what the atoms are, how they're interacting with each other, we can see regular spacing between the base pairs within a strand. And we can also see perfectly aligned, so it's directionality to maximize hydrogen bond interactions. So between the base pairs, complementary pairs are here, and then bases within a single strand are actually lined up, so they're stacked with pi-pi stacking. So that helps when it's slightly offset like that, get it into that helical shape. Crazy, right? That instead of being perfectly offset, that would have the strands like so. It would look like this. Look like a ladder. DNA doesn't look like a ladder. And that's partially because a combination of the hydrogen bond alignment and the pi-pi stacking needs to be a little bit offset to be optimized. So instead of being straight on, for DNA, it's offset a little, which every time you do that around the next bend, you get a helical turn. Very cool. So we don't have that. We have actually helical turn, thanks to those two small interactions that don't seem like such a big deal, make a big difference in the bulk structure. So when we're looking at it from the side, we see the pi-pi stacking interactions going on between base pairs of the same strand. If we want to get a better look at hydrogen bonding, I'm not going to spend a lot of time on that because that is not the point of this chapter. We've looked at that before. You will probably look at it again, but I'll just point out one. We'd have to rotate it a little bit toward us just so we can see differentiate between these atoms that are kind of look superimposed here. So if you rotate a little bit towards you, I'll just point out a couple of them. So notice the nitrogen here found in NH. That's allowed for hydrogen bonding. NH and N. Is it NH2? I think not. So I'm going to draw the H in the right spot. NH and an N. That is a hydrogen bond. Remember NH-OH with another NH-OH-H. No CHs. It's not polar enough. So NH-OH is all you'll see. Technical definition of hydrogen bonding includes FH, but we almost never see that. It's not in DNA. So for most of the time, it's NH and OH is what you have to worry about. So there's a hydrogen bond. This carbonyl has its friend here lined up, that NH2. By the way, N is blue color, if you didn't remember that, in the model kits. O is red. That's how I could quickly kind of see that I was working with a carbonyl here and the NH2 group here. And this guy's friend looks like it's blocked here. But who am I working with here? So looks like I have an adenine because I have an NH2N, right? So let's look at our structures again. NH2, N, carbon, N. Let's see if we have that pattern. NH2, oops, where are you? NH2, N, carbon, N. Yep, so this is adenine. So I'm just going to call it A. We know that adenine likes thymine. So let's hope that we found thymine over here. Carbonyl, NH, carbonyl. Thymine. Can we find that pattern? Carbonyl. Oops, let me bring it down a little, it's out of the screen. Carbonyl, NH, carbonyl. Bingo, we're good. So we have found adenine and thymine. So you can get a lot out of these molecular models. You want to be able to identify what's going on there. You want to be able to go to a three-dimensional interpretation. You want to take a three-dimensional interpretation and understand what that three-dimensional structure is showing you. So we'll use these a lot in this class. So I'm going to label this thymine. Okay. So notice that was the question to prompt you. Adenine, we found it. So good. It looked like a maze of atoms in there, but we found it just by looking for patterns. Has hydrogen bond, intermolecular forces with, that's the interaction with thymine. And pi-pi stacking interactions with whatever the DNA sequence is. Who's next to it? I don't know. We got to go. We'd have to figure that out. So in this particular strand, what do we see here? It's like, okay, what is it pi-pi stacking with? So in other words, this was our adenine right here. Who is here and here? So if we look above, going back to this one, notice that it helps go back and forth between the sides. We have a mystery base that's pi-pi stacking. So I'm going to ask that you try to figure out what it is. Maybe pause the video, take a minute to think, okay? Before I spoil it, because I'm going to use the same logic I did to figure out this one. I'm just going to go through the different iterations of this. You can use a 3D video that I'm supplying as well if you need to. Okay, so maybe you're pausing. Get that answer down. Go hit the pause button if you haven't, because I'm going to put the answer. All right. So you need to at least check it to make sure that made sense with you. Turns out they're the same above and below. This model had guanine above and below, so hopefully you got that one. Okay, so DNA, obviously, very important biomolecule. That's just one of many applications of aromatic pi systems, and we're not done with DNA. We haven't even looked at other parts of it, but the part of DNA we want to know, you don't need to draw it from scratch. What do we want to know with DNA now is where can we find pi-pi stacking interactions? And can we identify the bases based on maybe the structure and their aromaticity and how they're aromatic, right? Prove they're aromatic. So that's what we're focusing on, the base pairs, the aromaticity, and how that affects the structure of DNA. We're not looking at the backbone, and minimal focus on hydrogen bonding. We just kind of use it to figure out what goes where. Next application. These applications are actually really cool. Dyes have a rich chemical history. So a lot of people think of chemists, modern day chemists, as like drug makers and maybe rocket fuel formulation, that sort of thing. However, a really, really lucrative industry back in the day was dyes. So actually even the Victorian era, mauve was all the rage. That's why purple, I guess, ultimately became the color royalty. It was very hard to get that color in a dye, and it was synthetically made by Perkin, and then it was in hot demand. It was actually called mauvine or mauvine, and they called it mauvine measles. It was like just all the rage to have that. I almost said an epidemic. I don't want to use that word. Not these times. It was all the rage to have, mauve is the color that you're going to use. My idea of mauve is more pink, but the original color, mauvine, is like a royal purple. In fact, I'll show some pictures soon. How do we get these dye molecules? They come from aromatic systems, and we have to rely on information we already know about the aromatic systems to understand why we get a dye. And it's based on actually conjugation more than anything. So remember, if you increase conjugation, you decrease the energy of a molecule, which increases its stability, which decreases its band gap, which allows us to have a colorful sample. And I'll just put several colors: visible range, light, absorbed, and observed. So highly conjugated molecules, colorful. Less conjugation or no conjugation, we're not going to be absorbing in that range. So less conjugation, higher energy. which means less stable, which means a bigger band gap. The band gap is the delta E between the HOMO and LUMO. Just in case we didn't use that word last time. Boring, colorless, white samples that we're used to. So either colorless if it's like a liquid or white if it's a solid. So it's kind of exciting to see a colorful sample because it's not actually that common. But since all aromatic compounds have to have conjugation or continuous conjugation slash overlapping p orbitals, has to have some conjugation at least. Many larger aromatic pi systems have color. So once you get to larger ones, here's two really famous examples. Indigo and mauvine. So indigo is really well known because it is that color. We have it in the rainbow, even though we don't use that word very much. Roy G. Biv, blue, indigo, violet. But it's almost exclusively reserved for blue jeans. Your blue jeans, when they're brand new, that color is referred to as thanks to the molecule indigo. So most of you have blue jeans. So here we go. Just put that there to help you remember that we're talking about dyes. But you can see that extended pi conjugation, every single cart, it's planar. We have every atom, carbon or not, that's part of a ring is using a p orbital to extend this conjugation. And so we have a lot of highly conjugated, and we have both rings aromatic. And so that allows us to have so much conjugation that we're now in the color range. So this is really kind of a review of conjugation. We're just confirming that aromaticity and conjugation kind of go together when they're in ring systems. So here's another ring system, aromatic with extended conjugation that leads to a color. There's the famous mauvine A. I have a picture of that one I took from a website with the museum where they had to run an original dyed silk sample of it. It's very pretty purple color, not like what we normally see. So it's called Perkin mauve. So a piece of silk was dyed by Sir William Henry Perkin in 1860 and presented to W.M.J. Matheson October 8th, 1906. And there's his signature. So that's a pretty big piece of history there. And then I guess the Queen, all the royalty wanted to have everything in purple after that because it was just so hard to do, such a big feat, so novel. Okay, so that's kind of a fun, famous part of chemical history. But you know, that's got more of a cosmetic application, which sells big. It was big business. So there's no reason to, you know, look down on that. But there are some other examples of applications that might not sound as glamorous, but they have very, very high utility. And that would be nanomaterials. So I'm going to move this up. And this is an exciting section. So colors, just one level of extended conjugation. But when you go past that, it's so conjugated that the band gap between the HOMO and LUMO is super tiny. Then it's actually like the suddenly all those orbitals that were previously inaccessible get closer and closer together. And it's like, even though they're empty, the electrons have way more space to travel. And so when you decrease the band gap like that, you actually make it easier for the electrons to delocalize even more. And so big conjugated ring systems can actually be conductive. So they can be used as molecular wires. So I'm putting three famous, so they could either be like a semiconductor that's getting there, so pretty small band gap, or even tinier band gap would be fully conductive. So some good conductors. This is a famous one. This is a C60 version of carbon. Like carbon could be diamond, graphite, right? Coal, amorphous solid, but it could also be Buckminster Fullerene, buckyball. It's named after the architect that modeled building after the structure, Buckminster fullerene. So fullerene are these carbon like nano cages. It's actually a truncated icosahedron. So an icosahedron that had its points cut off, resulting in a pentagon surrounded by hexagons, just like a soccer ball. Pick up a soccer ball and look at it. You'll see the exact same pattern. Every time you find a pentagon, you'll see 6 hexagons surrounding it. Incredible symmetry. So incredible, in fact, that even though there's 60 carbons, it's only got 1 signal in its carbon NMR because all of the carbons are equivalent. So very misleading carbon NMR. I'm not going to write that because that's kind of interesting. 1 signal in CNMR because of the symmetry. So it has the hexagons fused to all sides of a pentagon, just like a soccer ball. Properties. Because of this extended, all those rings are aromatic. Extended aromaticity and conjugation make it very stable, low energy, small band gap. So it's actually conductive, and it's very strong. So applications, molecular wires, you can string, and lots of other applications too. Anything that is useful for its conductivity or its strength is also useful. You could think of using a buckyball in that way. Molecular wires is an exciting field because our wires are not molecular currently, like in your phone and other devices that have any wiring. They're microscopic scale. So if you can actually shrink from micro to nano, that's dividing the size by 1,000. That means your phone can be 1,000 times smaller if you're using molecular materials. We're not there yet. It's still active field of research. Next one that's worth considering, very similar, another version of carbon called a carbon nanotube. And there's different versions of it, but it's aromatic fused ring systems. So they're all 6-membered rings and into that cylindrical shape, like a tube. So these have an incredible pi-pi stacking. So it's greater surface area than a sphere, right? Cylinder. So these are extremely strong, high tensile strength. Oops, I meant to put that here. So lots of pi-pi stacking. And they're conductive. So they're useful for molecular wires. They're also currently used in tennis rackets because of their strength and body armor like bulletproof vests. Okay, so those are carbon-based nanomaterials. This one also it's a little different. It's a polymer, but it has a heteroatom in it. And it's made of connected heterocycles that are aromatic. So this is thiophene. And if you have 1, 2, 3, 4, 5, 6, and they're all connected at this, what's called the alpha position, so it's alpha sexythiophene. So the features said it's also conductive. So notice that we're not constrained to just the ring. It's conjugated because this is using a pure orbital, that's using pure orbital. It goes throughout this whole linear strand. So it's got promising applications as a molecular wire as well. Now notice it's shorter, it's not as extended as the other one, so it's actually got more of semiconductor features. These things could all be measured, but we won't go into that. But connected aromatic thiophene units. So that heterocycle that's like a furan only with a sulfur is called thiophene. So its most common application is to possibly use it as a molecular wire as well. So that's sort of a physical, organic realm of chemistry, where we're not really concerned about the pharmaceutical pathways or applications. It's strictly these types of chemists work with the engineers to come up with the right design for some of these. But that's all I want to do with applications, and I don't always get to go into it with some of them, but the aromatic system has such interesting ones, it's worth bringing them up. But knowing that, we'll summarize this, how the structure allowed us to have this interesting function that we find in these applications, that's kind of what we want to take away. Aromatic compounds are planar. That allows them to have those pi-pi stacking interactions. That strengthens the material. So we see bulk properties repeatedly where it's strong because it can have such extended pi-pi stacking. We also see that it's aromatic, and then if we have multiple aromatics, we have longer delocalization, which means possibly conductive material, right? So semiconductive, also colorful. I'll write that instead actually, because that would be the first, it's colorful. And then more extreme cases where it's more extended aromatic ring systems, conductive. So semiconductive would be in the middle. Very cool, right? So fun to talk about those. What you want to know is that last bit. How was it able to be conductive while extended delocalized electrons, right? How was it able to be colorful? Same concept with conjugation, right? So those are the things you want to keep in mind. The structure-function relationship, you don't have to memorize structures of individual ones, maybe just recognize them. Okay, so now we're going to get to the meat of it. How is aromaticity giving rise to such stability? I'm going to leave you with a thought before I start. Think about the fact that 4n plus 2 conjugated pi systems should be, we know they're incredibly stable, but why? And why are they so much more stable than 4n? What's wrong with 4n? Since when was that a crime, right? They're conjugated, so aren't all conjugated molecules stable? What is determining this energy? It feels so arbitrary. Huckel says it's stable, and if it's not Huckel, it's like criminal. So that's really not the case. The answer comes down to what's happening at the electronic level, the orbital level. So I'm going to have you think about drawing molecular orbital diagrams, review your conjugated pi systems, and then we're going to do that in a cyclic fashion. So you're not ready to move on to this if you have not worked through this for acyclic cases, the conjugation section. So pause a minute, go back and review, and then we'll start this right here when you've had a chance to do that. So make sure you're up to speed on that, because otherwise it'll get confusing, because we're relying on that as a foundation. Okay, see you soon.